Welcome back to the course Corrosion Protection Methods. Let's start lecture 38. Today we'll start a new segment for corrosion protection, which is called inhibitor. Now, if we look at inhibitor, as the name suggests, that it inhibits corrosion. So, that is what those substances are called inhibitors. Those are generally added in a very small quantity to the electrolyte. At times, it is also incorporated along with the coatings. So, those inhibitors either influence the cathodic reaction or influence the anodic reaction, or sometimes they form a film, or at times they can actually remove some of the corrosive agents like oxygen, or at times they can also reduce the hydrogen ion concentration. So, we will try to look at some of those aspects, as well as we will try to look at how to calculate inhibition efficiency of those substances towards protecting the metal surface from corrosion, as well as also we will try to look at what could be the amount of inhibitor that is to be added and corresponding cost of it. Now, when we talk about inhibitor, that inhibitor we have to see some of those aspects or some of those characteristics when something can be called as inhibitor. So, if we talk about inhibitor, so first one is it is a chemical substance, either organic or inorganic, and that is added in a small quantity. Addition, and that the small quantity either in terms of concentration or in terms of kg to an electrolyte. This can be added to electrolyte, or we can say environment to which this metal is exposed to. And also sometimes they can be incorporated along with the coatings. And they actually substantially reduces the corrosion rate. So, this is basically acting like a catalyst. And interestingly, most of the time this inhibition efficiency is mostly trial and error with some prior idea about the metal surface as well as the environment, as well as those components what we are adding to. So, we have to do experiments. And then we can find inhibition efficiency, and in most of the time they are proprietary. Most of the time the companies do not disclose the composition of it. Now, these are some of the characteristics of inhibitor, and when we talk about organic or inorganic, they can have low or high vapor pressure, will see later that there are some inhibitors which actually uses this principle of high vapor pressure. What happens if you keep that inhibitor close to the metal surface, and then because they have a very high vapor pressure, they can uh, evaporate or sublimate, and then later on the metal surface they can redeposit back, or condensation happens. And when condensation happens, that surface is covered with that inhibitor, and that actually prevents the contact between metal surface and water. Since we know for aqueous corrosion, water is one of the species which actually leads to a good amount of corrosion in metal surface, on metal surface. Now, like for example, if you have moisture, if you have oxygen, then oxygen reduction can happen. So, that would lead to a great degree of corrosion of iron. Now, if you remove moisture, then corrosion rate can reduce provided the room temperature or the temperature is low. See, if you go to a high temperature, even if you remove moisture, there could be possibility of corrosion in the form of high temperature oxidation. Now, further we can talk about some of the other aspects, how to choose an inhibitor. Okay. So, we can say choice of inhibitor. So, that will be decided by some of the characteristics to be considered. One is, we need to see how much corrosion protection we want, and whether we are looking for corrosion protection locally or uniformly. So, that means magnitude or extent of suppression. And now, when we talk about corrosion, more generally there are two types, one is uniform type, another one is localized. So, we need to know beforehand what could be the extent of protection we want. Second is the inhibitors should be durable. It should provide long effectiveness or protection. Third is there could be this inhibitor temperature, pressure, then galvanic coupling. So, those actually can influence the inhibition efficiency. Then we can also have some influence of inhibitor on the physical functions of that particular equipment. For example, inhibitor can actually affect heat transfer in cooling water system. So, that we have to keep it in our mind before using inhibitor. Then of course, these inhibitors are organic and inorganic substances, and many a times they are toxic to the environment, as well as if it is seawater, then it is seawater species. Even it can also lead to influence on the human lives. For example, chromates. So, we use this chromate is considered to be one interesting inhibitor But chromate is also carcinogenic because if it is CR6, so it's toxic. Similarly, uh, N2 amines are toxic. For example, arsenic, it is also used for protecting metal surface. This is one of the cathodic inhibitors. We will talk about that. So, we have to consider toxicity as well as pollution problem. So, the inhibitor should possess low toxicity and it should not pollute the uh, environment. Less polluting tendency. Now, finally, many of the inhibitors are very costly. For example, one of the inhibitors which is considered to be anodic inhibitor, molybdate. So, molybdate inhibitors are very costly, but they are very effective anodic inhibitors. They can reduce the corrosion rate to a great extent of steel. So, we have to also look at the cost factor. That cost factor will be also decided the durability of its use or the prolonged effectiveness of those inhibitors in reducing the corrosion rate, as well as the dose of those inhibitors. So, now we have to also look at dose as well as cost. So, that will decide the economic use of inhibitors. Fine. Now, we have been talking about inhibition efficiency. Now, we can actually calculate inhibition efficiency, and that should be calculated on the basis of experiments. So, there could be two ways one can do experiment. One is you mix inhibitor with the electrolyte where that particular metal will be exposed to. You dip the metal, wait for some time, take it out and see the weight loss. In one case, you do not add inhibitor and then see the weight loss for a particular specific time, and then you have two corrosion rate values. So, one corrosion rate is we can consider to be blank, that means where we have not used any inhibitor, the other case which is inhibited. Now, that two differences divided by the corrosion rate without inhibitor, we can get the efficiency. So, efficiency of inhibitor can be written as corrosion rate without inhibitor minus corrosion rate with inhibitor divided by now. Interestingly, this particular efficiency can also give us few more information. One is temperature effect, pH effect, then other chemical presence, then CO2 presence, SO2 presence, all those situations as well as dose. So, that means amount of inhibitor to be added. So, we can get all those effects on the inhibition efficiency by doing experiment. For example, if we want to do experiment for a particular dose of inhibitor, let us say we want to see what will be the effect of inhibitor on the inhibition efficiency. if we have low temperature as well as high temperature. Let's say one temperature is 20 degree, another temperature is 50 degree, we can actually calculate by doing a simple polarization experiment. Okay, so we'll see that. Now, this corrosion rate can be calculated by simple polarization or by immersion test. Now, if we do polarization in a test, let's say if we do TAFL and let's say the TAFL plot looks like this. This is E volt log I, which is ampere per centimeter square. Let's say this is in terms of volt. This is E core. Now, if we check the corrosion rate, what we can do? We can take we just take the linear portion if we want to do TAFL. So, I take a TAFL slope here and another TAFL slope here. So, this is my E core and this is my I core. Okay. Now, let us say this is when it is no inhibitor. And for example, let us consider mild steel in 3.5% NaCl. Now, once we add inhibitor, then this particular diagram polarization plot can change. So, let us see what could be the change. So, it can either go this way or it can move other way. Okay. So, now we will check later on that why this particular polarization for the same metal when we add inhibitor, it moves this way or it moves this way from the E core of blank. So, let us say this is, let me put it as blank, and blank means it is no inhibitor condition. Now, those blue lines, this line indicate with inhibitor and this one also indicates with inhibitor. Fine. Now, that time we can again calculate the corrosion rate by doing TAFL extrapolation. So, linear portion, here also the linear portion. Okay. Now, this will be the corrosion rate inhibited. Okay. Now, on the case of the other curve, here also you can do TAFL extrapolation. Now, this is I core inhibited. Fine. Now, we can calculate the inhibition efficiency for both the cases. So, this is for this case and this is for this case. Now, we can do it like this. Now, I core blank minus I core with inhibitor. So, that means we are talking about this one divided by I core blank. So, this is my inhibition efficiency in terms of percent. So, I just multiply by 100. Okay. So, that becomes my inhibition efficiency. For the blue one, this I core would just change to with inhibitor. So, that means we are talking about this particular current density corresponding to the corrosion current density. Now, this is the simple equation which indicates inhibition efficiency. In fact, here we can also check what will be the efficiency for different dose if we fix the sodium chloride concentration as well as temperature. Now, you fix the dose, then you change the temperature and see what is the inhibition efficiency. Now, if you want a specific inhibition efficiency, then you keep doing experiments by adding or by adding more inhibitor or by changing the sodium chloride concentration. So, that will give us some sort of data sets that these are the conditions at which I could get this much of inhibition efficiency, this much of corrosion protection. You could see that if I core this particular with inhibition is very low, then of course, I could get a very high inhibition efficiency. So, even we can get around close to 90 to 97% inhibition efficiency. So, like one particular small set of data. So, I do not want to indicate how we got those data. This is experimental data. These are experimental data what we have found at IIT Kanpur. So, this is related to green inhibitors. So, one such example data sets. So, we are working on green inhibitor from different green substances like leaves, plant leaves, or some of the waste products which people have been exposed to, people are exposed to for thousands of years. So, that means the human actually has developed a lot of resistance to those substances. So, that means those can be, if we can get out those inhibitors out of it, then it will be considered as green inhibitors. For example, some of the inhibitors like chromates, nitrates, those are not very green. For example, they can actually create health hazards to the human as well as sea lives or water lives. Now, one such example is, for example, when we talk about blank. So, there we are simply using, or we can say, solution. So, and the solution is 3.5%, main ingredient is 3.5% NaCl. There we are adding inhibitor. Now, one case it is blank, and then we can actually find out E core. So, when it is blank, it is minus 0.71 volt, and this is with reference to saturated calomel electrode. So, this is the reference electrode what we use, where E naught with respect to standard hydrogen electrode, it is plus 0.241 volt. With reference to that steel, and here we are using mild steel. Okay, low carbon nominal composition mild steel. Now, that voltage becomes E core minus 0.71, and then I core, which is the corrosion current density as we have found here. So, that is 28.84. So, this is in terms of microampere per centimeter square. Then corrosion rate, if we calculate, you will get around 0.33 millimeter per year, and efficiency. So, here we do not have any efficiency because this is the blank. Now, if we talk about some addition of those inhibitors, green inhibitor into the same solution, we get the voltage around 7.72 volt, and that time corrosion current density drops down to 1.86, and it corresponds to 0.022 millimeter per year. And efficiency, now we can calculate corrosion rate in terms of 0.022 minus 0.009 divided by 0.022, I should get, can you hold? So, here it becomes 0.022 minus 0.009 divided by 0.022. Just a minute. Zero 0.33 divided by 0.022, and it will be here 0.33. So, 0.33 so it's close to around 93.3%. So, here you have to multiply it by 100. So, then you will get in percentage wise. So, that means we could see that the efficiency, which is the corrosion rate with blank minus corrosion rate with inhibitor divided by corrosion rate without blank. So, this I core, what I am talking about, so you can also should see this. So, if you use I core, you should get the same values. Okay. Now, if we talk about another dose level, so we have actually increased the dose level. If we go to S3, which is a little higher dose, the potential goes to 7.3 volt and the current value goes to 1.48. So, that time corrosion rate becomes 0.017, further reduces, and the efficiency, the way we have calculated here, it will go to 95%. So, like that way we could see that how to calculate efficiency and how to see the effect of dose. But remember, the dose should be as minimal as possible, because inhibitors cannot be added to a great extent because it will influence other aspects. For example, if it is cooling water system, the inhibitor can actually influence heat transfer efficiency. So, we should add as minimum as possible, but at the same time we should also look at this inhibition efficiency, that the effect on corrosion rate, it should reduce drastically. Fine. So, this is one set of data which is IIT Kanpur data, one group. Our group is working on this green inhibitors. Okay, so let us look at the scope of inhibitor. So, we can actually find a lot of application fields where inhibitor can be used. One is corrosion of cooling water piping system. Like heat exchangers or distribution line. Boiler corrosion can be reduced using a small dose of inhibitor, like removing CO2 or oxygen by water treatment. Deposit may also form by suspended solids. So, that can be avoided. Okay. So, like removal of O2 or CO2, those kind of dissolved gases can be removed and boiler corrosion can be minimized by the usage of inhibitor. Petroleum industry heavily uses inhibitor. So, they are mostly filming amine or propylene dramine. This kind of inhibitors are used there. Potable water system, where we can use calcium bicarbonate or polyphosphate. Then engine coolant inhibitor is used, where we can make use of sodium chromate or borates, nitrites like sodium nitrite. Those are the things can be used for reducing the corrosion of the container or the engine. Packaging industry, mainly vapor phase inhibitor. So, like one example is cyclohexylamine or methylamine. Hexamethylamine. So, those are the substance used for protecting packaging, protecting for packages, package materials, vapor phase inhibitors, mainly used for machineries which are transported through sea line. Then we can also use in construction industry, mainly chromates, nitrates or sodium metasilicate. So, these are used to protect rebars from corrosion. So, these are the scopes. In fact, at times inhibitors can find inhibitors uses can be limited in those some of the applications field. Okay. So, now we could see that inhibitors are basically some substance which are added at a very low dose to an electrolyte, and it reduces the corrosion rate to a great extent and gives or uh, uh, provides protection to the metallic structure. So, we will talk more on this inhibitor. So, we will try to classify inhibitors and try to understand the mechanism how it works, and then finally, we will also try to calculate the dose amount that is to be added to the electrolyte for a specific amount or specific degree of protection. So, let me conclude today's lecture, and we will continue our discussion on inhibitor in our next lecture. Thank you.